In every partially filled container of a liquid, the space above the surface contains the vapor of the liquid. Now, how does it get there? In the liquid, there are many molecules very close together and in great agitation. Some of these molecules have greater energy than others. And if the energy of a molecule is great enough, it may escape from the surface of the liquid and enter the space above as a gas. We recognize this as evaporation and feel its effects when the water on our bodies evaporates after a swim. If we cover the container, the gas soon fills the space above the liquid and exerts a pressure on it. If the liquid's water, we call this gas water vapor. The pressure of the gas can be measured. This is called the liquid's vapor pressure. The experiment that you'll see now was performed in 1974. Back then, the closed conventions were different, and so were some conventions of scientific terminology. So you'll hear the experimenters referring to degrees centigrade, which was common back then. Now, of course, we say degrees Celsius. Let's check into that lab now, where they begin by looking at the vapor pressure of pure water. What we'll do today is somehow isolate the vapor, the water vapor that's above the water, and measure its pressure. Now, of course, the first job that we're going to have is to isolate that water vapor. Because if you consider now, although there are molecules of water in this container, there is also another gas in the container. And what is that gas? It's air. In fact, the concentration of water vapor in the air at this point inside this flask is very, very small. So our first job will be to get rid of all the air and then measure the pressure that the water vapor exerts inside the container. Now, in order to do that, we've set up some equipment over here, and I'll show you the various parts of it. First, we have a pump in this area here. The pump will evacuate all of the air that's inside this flask. Now, it may be a bit difficult to see, but this flask contains about 100 milliliters of water. After evacuating the air from that top portion, we'll allow the vapor from the water to fill the container. Now, what do we mean by fill? Does it just keep on giving off water vapor continuously? Or do we come to a spot where we can say that we've got all the water vapor that could possibly be in that container? Well, the latter is true. In the same way as one can consider that a molecule of water in this flask can have enough energy to escape into the top of the flask, it's also possible that some of the molecules that are circulating around the flask in the gas phase might lose energy and enter the water again. Well, at the very, very beginning, a lot of molecules are escaping from the water into the flask. As the flask starts getting filled with gas, more and more of the molecules in the gas phase start entering back into the water. Eventually, a situation that's called an equilibrium situation is reached, at which point, for every molecule of water that escapes to become a gas, there is one molecule of water that re-enters the liquid phase. Okay, we will now close the system off and evacuate. Now, this is a manometer. It's a special type of manometer. It's called a closed-end manometer. It works a little differently than the open-end manometer that one sees a bit more often. In order to read this particular manometer, which will give you the pressure of the gas inside that flask, one looks at two portions. There's an inner tube inside that contains mercury, and there's an outer tube that contains mercury. The pressure inside this flask will be the difference between the height of the inner tube and the height of the outer tube. Right now, all we're doing is flushing out the flask. We're getting rid of all the air and, of course, whatever water vapor happens to be in the flask. Let's check and see if we're down as far as we can go. Yes, I'd say that we've got about as great a degree of evacuation as we'll get with this pump. Now we're going to close the system off by squeezing this pinch clamp. Okay, the pump is now not working on the system anymore. I'll turn the pump off, and the system is completely closed. You see, it's closed at this end, and it's closed at this end. Now we'll have to wait, maybe 5 or 10 minutes for all the molecules inside that flask to escape into the upper region. Not all the molecules, but of course as many molecules as one can get in there until equilibrium is reached. Well, the system has equilibrated now. We're getting a constant pressure reading. And to read the pressure and the temperature, we've got Sam Valora here. Sam, would you read the pressure for us? First, give me the reading in the inner tube, and then the reading in the outer tube.
The inner tube is 25.
25 millimeters of mercury for the inner tube, and the outer tube is 11 millimeters of mercury. And the temperature?
Temperature is 20 degrees.
20 degrees centigrade. Okay, fine. Now, I've entered this data on the blackboard in much the same way. I've made this chart up to look very much like the charts that I've handed out to you. So while we're taking the data, you repeat the data, and well, I'll tell you what you'll have to do with it at the end of the demonstration. Okay, we have a vapor pressure, which now will be the difference between the height of the mercury in the outer tube and the height of the mercury in the inner tube. 11 from 25, 14 torr is the vapor pressure of water at 20 degrees centigrade. But now it'll be very interesting to see what happens to the vapor pressure as we heat the water in that flask. Does the vapor pressure stay the same? Well, think about those molecules in there moving around very quickly. If I heat the water, I'll be putting more energy into the system. That means that more of those molecules will be energetic, and we can expect to find more of those molecules entering into the vapor phase, into the gas phase. So, and if that should happen, we would expect to find a higher vapor pressure. Okay, let's add some hot water to the system. Now let's stir it up a bit to make sure that that hot water is mixed in there well. And I will take a quick temperature reading just to see if we're in approximately the right range, and we are. Okay, now I'm just going to repeat the process that we had before. First, I'll get the pump back into the system by opening this valve. Okay, again, we're evacuating the system. Okay, now let's shut the pump off again and let the system equilibrate. Okay, this will take another 5 minutes or so until the water vapor starts filling the top of that flask and reaching equilibrium. Okay, we've reached equilibration for the second time now. Now Sam can come back in and read the mercury heights and the temperature. The inner tube first.
The inner tube is 37.
37 millimeters of mercury. The outer tube is 10 millimeters of mercury. And the temperature is 31 degrees centigrade. Okay, let's warm it up a bit more. We'll heat it up a bit more so we can get 3 points. But we can draw a nice curve with the results. Okay, again, we flush the inside. And while that's flushing, we can add some more water. Stir it up. Okay, that should be about the right temperature. Now let's close the system off again. And we can turn the pump off. And now we'll wait another 5 or 10 minutes for the molecules to reach equilibrium above the liquid. Well, we've reached equilibrium again, and it's time for Sam to take another reading. Sam, you read the manometer and the temperature for us. The inner tube.
The inner tube is 45.
45 millimeters of mercury, and the outer tube
Is
8 millimeters of mercury, and the temperature
35 degrees.
35 degrees centigrade. So at this point, if you take a look at the chart, you see we've got values for the mercury height in the inner tube and the outer tube at the 3 different temperatures, and this is what your chart should look like, the ones that that you're filling in right now. I've left out the vapor pressures. That's just a matter of subtracting these two values and entering them in there. Okay, what are we going to do at this point? It'd be interesting to see what effect we would see if we put something into the pure water. Remember now, we've been doing this with pure water. We've been finding the vapor pressure of the pure water. What would happen if we put some sodium chloride in that water solution? I have here approximately 9 grams of sodium chloride. And what we're going to do is take the sodium chloride and very carefully place it into the flask. Sam, could you come over here and hold this? Get on the, if you get on, there you go, good. Okay. Okay, sodium chloride right in the flask. Let's stir it up so that a good portion of it will end up in solution. There it is. I think we got all of it in. Okay, all of the sodium chloride is in solution right now. And now we'll rerun the experiment. Now, during the break before, we got rid of the hot water, and we started off with cold water again. So the temperature is in the 20-degree range. Don't take that down yet, because we have to wait for equilibration. Okay, the valves are shut. Now we evacuate the system. You see the boiling occurring again? Can you see that? Again, there's boiling. And notice, I'm putting my hand right in there. It's cold. It's cold. You're watching water boil at a temperature well below 100 degrees centigrade.
The normal boiling point of a substance is the temperature at which the substance will boil when the pressure is 760 torr. For water, this normal boiling point is 100 degrees centigrade. But as you can see, liquids can boil at temperatures below their normal boiling point if the pressure is reduced. The water in the flask is at 25 degrees centigrade, and it started boiling when the pressure dipped below 24 torr.
Boiling is still occurring. We're still evacuating the system. The boiling has almost subsided. Okay, the system has now equilibrated, I think. Shut off this valve and turn the pump off. Okay, now again we're going to wait for equilibrium to be achieved above the liquid. Equilibrium has now been reached, and we're ready for Sam to take his readings. The height of the mercury in the inner tube.
27.
27 millimeters of mercury. Height of mercury in the outer tube. 10 millimeters of mercury. And the temperature. 25 degrees centigrade. Okay, again, we're going to be interested in what effect warming up that liquid, that solution, warming up that solution, what effect that will have on the vapor pressure. Okay, let's flush out the system again. And add some boiling water. Stir it a bit. And close the system off to the pump. Again, we'll wait for equilibration. Equilibrium has now been reached, so Sam can take another reading. Sam? The height of mercury in the inner tube. 35 millimeters of mercury. Height of mercury in outer tube.
Outer tube,
9 millimeters of mercury. And the temperature. 35 degrees centigrade. Okay, this will be our final reading. Again, we'll flush the unit out, add some more hot water to heat up the solution in that flask, and then we should have enough data for two very nice curves. Stir it up again. And close the system off to the pump. Okay, we're reaching the point where we're taking our final equilibration before our final reading. Sam will now take the final reading. Height of mercury in the inner tube.
43.
Height of mercury in the outer tube.
9.
Temperature.
38 degrees.
38 degrees. And here we have our final chart.